Number 23 and 35 both deal with expected value. And for a binomial probability, the expected value formula is just n times p, where n is the number of times you're running the experiment and p is the probability of success for whatever success is defined to be in the given problem. So for 23, we run the experiment 200 times. We select 200 random mortgages, and a success is if the foreclosure came from California, and the problem tells us the probability of that is 0.34. So just multiplying these together will tell us the expected number of foreclosures to come from California out of that stack of 200. For 3, 5, or 3, 7, and 9 on page 582. So this is number 1 here. In order to be a probability vector, and vector is just a fancy name for a matrix that has one row. So the numbers in this row represent events happening, the probabilities of them. So in this example, I just named 2 events, A and B, and A happens 1/4 of the time and B happens 3/4 of the time. Well, all that needs to occur for this to be a legitimate probability vector is that they add up to 1. One event has to happen or the other, so all the events together should add up to 100% or 1. And the same thing with these transition matrices. The first row represents the probabilities associated with event A. So if you're in a given state, you either have to remain in state A or transfer over to B. So it should add up to 1. This should account for 100% of the people who were in state A, and it doesn't. So this would be an example of a not a transition matrix. Each row should add up to 1. And in addition to that, make sure all the probabilities are actually legitimate probabilities. For example, I can make something that adds up to 1 here. 1.25 and negative 0.25. But this isn't a transition matrix because this isn't even a probability. It has to be a number between 0 and 1. So check that all the numbers are between 0 and 1, and then each row has to add up to 1. So for number 33 on page 583, it's a story problem about people favoring or not favoring a casino gambling initiative. And it tells you that out of the people who favored it, so let me read this. Among those who did not favor it previously, 30% now favored it. So start down here. People who said no previously, now 30% of those changed and they favor it. Well, what does that mean? How many no's still say no to the gambling? 70. And then the next sentence says, among those who favored the initiative initially, 90% still favored it. So they were in favor. And then how many stay in favor? 90%. So how many switch over to no then? 10%. So that'd be the matrix you need to set up. And then let me shift this over, to actually, I am having trouble. There we go. All right, to actually do part B, find the percentage who favor the gambling initiative after the media blitz. So the poll said that 35% planned to vote for it. So 35% were in favor. Well, how many plan to not vote for it then? What would that be? 6.5? Alright, so let me rewrite this. So you take this is where we are. Our current state is 35 in favor and 65 say no. And multiply that by the matrix, and the answer, whatever it equals to, will be, it'll be the answer to part B. What's our new state? What have we transitioned to from this We do all our transitions, and now how do people feel? It's going to be different than 35% yes and 65% no. And then for the long-term prediction, we say, well, we don't know how many favor it, how many don't. But eventually in the end, the number that favor it and the number who don't is going to be the same after we do all this transitioning. If these numbers all stay the same in the long term, you take this and multiply it by the matrix, and it's going to equal the same exact thing. And I'm going to run through, I think your last question was number 22 on page 583, and I'm going to run through that one, which shows you the steps of how to solve something like this, and then you could use it to solve 33. So number 22, page 583, is about finding the equilibrium vector or steady state vector. So basically, you have a breakdown from people who are in choice 1 or choice 2, and then after we do the transitioning, it's the same exact breakdown, the same exact numbers for choice 1 and choice 2. So to solve this, start with matrix multiplication, where you take this row and you multiply it by the first column. So that would be 0.3 times the x plus 0.4 times the y. And now we can't really add those together because we don't know what x and y are. So we would have to just write it like that, 0.3x plus 0.4y. And then you take that row and multiply it by the second column. So you get 0.7x plus 0.6y. And so all we've done is reduced this left side of the equal sign by doing matrix multiplication, and the right side of the equal sign stays the same. We haven't done anything on the right side. So now we have two matrices. They both have two entries in them. This is one entry. We can't actually add it together and get a number because we don't know x and y, but it's just one entry. And here's the second entry. And on the other side, we also have two entries. Well, if these matrices are actually equal, then the first thing on the left side has to be equal to the first thing on the right side. And similarly, the second thing on the left side has to be equal to the second thing on the right side. So we get these two equations. Now you only need one of these equations going forward, and I'll just take this one. Okay? So you only have to pay attention to one of them to get your final answer, and we'll just work with this one. So one thing we can do is we can combine the y's in this equation. So this is a y over here. If it helps you think about it, it's a 1y. So subtract 1y from both sides to get all the y's on the left. So 0.7x, and if we take away 1y, we're going to have negative 0.4y. And you take away 1y from here, 1y minus 1y leaves you with 0. 0.6 minus 1 leaves you with negative 0.4. So here's our equation. Now we need to use a substitution. Because we have two variables, we got to substitute. And so think back to like questions 1 through 6 of this section. These numbers have to add up to 1, whatever x and y are. You know, maybe it's 30% and 70%. Well, that adds up to 1. Maybe it's 80% and 20%. That adds up to 1. Whatever they are, these two numbers have to add up to 100% to be a legitimate probability vector. So we know that x plus y has to equal 1, or 100%. Well, we can use that. That means x equals 1 minus y. Just subtract a y from both sides. X equals 1 minus y. So go ahead and substitute that in now to where we are. 0.7 times 1 minus y minus 0.4y equals 0. So the numbers are going to change from problem to problem, and when you do the matrix multiplication, you get different answers and stuff, but this will always be the same. You will always be substituting 1 minus y in for x. So you substitute that in for x, and now you have just one variable and you can solve for y. So let's distribute here. 0.7 minus 0.7y minus 0.4y equals 0. So we can combine that. 0.7 minus 0.11y equals 0. Add the 0.11y to the other side. And now divide both sides by the 0.11. And that's going to reduce to 7 over 11, or as a decimal, it's 0.6364. So if we know that's what y equals, well, remember what we've done up here. X plus y has to add up to 1. This has to be equal to 1. So we know the y part is 0.6364. So that means the x part has to be, what would that be? Let me get my calculator out. 1 minus 0.6364 is 0.3636. So if you use that number for x and that number for y, and you multiply it by this matrix here, you get the same exact number back. You'll get this back. And it may be off slightly because we rounded here, but if you use the exact fractions, it would be exactly the same. So we said y was 7 over 11. Well, if y is 7 over 11, x needs to be the percentage 4 over 11, so that it adds up to 1. If you took 4 over 11 and 7 over 11, you multiply it by this matrix, you will get back 4 over 11 and 7 over 11.